at a nice application of some ideas from the course, and in particular, in one of these cases, an application of further application of quadratic residues. So something everybody should know. If you've looked at the past examination papers, you'll appreciate why. Euclid's proof of the infinitude of primes. Bit of an awkward way of saying it, but there are infinitely many primes in the integers. We know that. We've got a fairly approachable proof of it, which we did in the first part of the unit. Everybody should be able to prove it. A quick proof of it is you assume only a finite number. Say P1, P2, up as far as PR. Those are the only primes that there are. It's wrong to say that because it's an infinite number, but this is how you prove it. So you pretend there's only a finite number, and you consider the number n, which is the product of them all, plus 1. By some fairly basic divisibility results, n has at least one prime factor. N is either a prime number or it has a prime factor. So there exists pi, one of these primes here, such that pi divides n. This is for some I in the range 1 to r, because we've assumed that there are only a finite number of primes. Every number is made up of primes. Prove that. So there's one pi that divides n, but then this implies that pi divides n, and it will also divide this product of p's because it is one of them. Pi is somewhere in this list of factors. So pi is going to divide this linear combination of those two, but of course this linear combination is equal to 1. Which is impossible. As pi is a prime number, so it's strictly bigger than 1. Okay. So it's this impossible bit, that the contradiction. So we've reached a contradiction. So it must be that somewhere along the way we made a mistake. Okay? So you can't have a contradiction. The thing that led to this mistake is the very first thing we said. Assume there's only a finite number of primes. Okay? Everything after that was, well, I won't say perfectly argued, but argued correctly. Okay? So what caused the problem was that first assumption. So there is not a finite list of primes. It's not a finite number of primes. Okay. That's like the, for you, that should be like the national anthem or something. You should just know it off by heart. You should be able to stand up and sing it whenever requested. As loyal subjects. Indeed. Do you know more than the first verse though? That's another question. Okay. Dirichlet's theorem is an extension of this. So we know there's an infinite number of primes in the integers. Dirichlet's gone further and said you will find an infinite number of prime numbers in every congruence class, modulo anything, provided that congruence class is not trivially consist of all composite numbers. So the way it's commonly phrased is, if the GCD of A and N is 1, if A is co-prime to N, then there are an infinite number of primes in the arithmetic sequence
arithmetic sequence, so the sequence beginning with A, then going A plus N, A plus 2N, A plus 3N, etc., etc. This is an arithmetic sequence, which is more or less, i.e., the congruence class of A modulo N. Or if A is positive,
Well, at least it's all the positive numbers in the congruence class of A modulo N. Yeah. These are numbers that are all congruent to A mod N. Now, okay, I hope once you think about it, you see the need for this GCD condition. If the GCD was not 1, if it was 2, or let's say it was 3, if the GCD of A and N was 3, well, 3 divides A and 3 divides N. So that means 3 divides every number on this list. So they're definitely not prime. Maybe if A was 3 itself, maybe the very first one would be prime, but everything afterwards is divisible by 3, so everything afterwards is composite. That's what I mean. If this GCD is non-trivial, then trivially we see that all the numbers are composite. But as long as this GCD is 1, so then there's no trivial reason why each of these numbers should be composite. Now, most of them will be. Most numbers are composite. But Dirichlet's theorem says there'll be an infinite number of primes. Now, we don't have the tools to prove this theorem as it's stated there. Okay? The general proof of this requires more machinery that we haven't covered. But what we can do is we can prove some special cases. Okay? Some special cases of this, i.e. particular A, particular N, some special cases of this we can prove with the tools available to us. So this is question 3, page 69. Right, question 3, it goes through this introduction to Dirichlet's theorem. And then it gives you some guidance in parts A, B, and C. It gives you some guidance for proving it. The proofs, they're all inspired by Euclid's proof that there's an infinite number of primes. Okay, they all take that as their inspiration. And it builds, and they kind of adapt the key ideas from here to give a proof. Okay? So the first case A we're going to look at is considering the case of 4n minus 1. So we're using the A as minus 1 and the n as 4. There are infinitely many primes of the form 4, I'll call it m so as not to confuse with the n there, 4n minus 1. So here I'm using the n equals 4. I'm adding a 4 on each time, and the A is minus 1. So. Now we certainly know a few primes of that form. 7 is of that form, 11 is of that form, 31 is of that form, no. Yeah, 31 is of that form, etc. So there's at least 3 of them. Primes that are 1 less than a multiple of 4. 27, oh no, 27 is 4. Okay. But how do we prove it? So there's some guidance given, or there's a kind of hint to get the argument started, given in part A. So let's suppose there isn't, okay? Suppose only a finite number. Now the proofs all work in slightly different ways. So the way it works is if there's only a finite number, then let P be the largest such prime.
largest such prime of the form 4m minus 1 for some n. Okay, we can talk about, if there's a finite number of them, we can talk about the biggest one. You can't talk about the biggest one if there's an infinite number of them. There is no biggest one, right? But if we pretend there's only a finite number, then we can talk about p, which is the special, well, it's the last prime of the form 4m minus 1. And then we consider a number specially constructed n. So this is like the n from Euclid's proof, except we construct it in a slightly different way. We're going to take all the primes up to p. So not just the ones of the form 4m minus 1, but all of the primes. And then we're going to subtract 1, and we're going to square the 2. Okay. Okay, and then we think of the prime factors of n. So we consider a prime factor q of n. First of all, we'll say that q must be bigger than p, right? Q must be bigger than p, because if it wasn't bigger than p, then it would be included here on this list. And then you would have q dividing n and q dividing this bracket. So that would imply that q divides minus 1. So q has to equal 1. So that's a contradiction. So it must be that q is strictly bigger than p, since otherwise q would divide n minus this funny bracket. Why does it divide the bracket? Because q is one of the factors along here. If q was less than p, less than or equal, i.e. q divides minus 1, which is a contradiction because q is a prime. So now we know q divides n and q is bigger than p. Everybody okay with that proof that q has to be strictly bigger than p? Yeah. It's because of the special way we've constructed this number n. So now we make some observations about what kind of number q is. Obviously, what we're gonna, well, not obviously. The way the proof is going to finish is that we're going to prove that q must be of the form 4m minus 1. That's what we're going to do. Okay. We're aiming to show that q itself is a prime number of the 4m minus 1, and that's going to be a contradiction because p was supposed to be the biggest one. But here we're going to encounter another prime which is bigger than p and which is also of the form 4m minus 1 for some n. That's a contradiction because we said p was the biggest one. So you can't have found another one that's strictly bigger than. That's the contradiction that's going to contradict our assumption at the start that there was only a finite number of these primes. So how do we prove that q has to be a number of this form? Well, firstly, notice that n is odd. That's not hard to see because it's an even number minus 1. Yeah? So n is surely odd. So q must be odd. You can't have an even number dividing an odd number. You can have an odd number dividing an even number, but not. Yeah. N is odd, so q is odd. Well, that implies that Q is congruent to 1 or 3 modulo 4. Now, it's the 3 we're interested in. This structure 4m minus 1 is congruent to 3 mod 4. Yeah? 3 is the same as minus 1 modulo 4. But it's possible, so I want Q to be congruent to 3, but what if Q was congruent to 1? So what we say is, it can't be that all the prime factors of Qn are congruent to 1 mod 4. Why is that so? See, n is the product of its prime factors with multiplicity if some primes divide it a number of times. So you get n by multiplying together all of its prime factors. But if they were all congruent to 1 mod 4, well, when you multiply numbers that are congruent to 1 mod 4, the result is again congruent to 1 mod 4. Yeah? So that would mean that n would have to be congruent to 1 mod 4. So it can't be that all the prime factors are congruent to 1 mod 4, as this would mean n was congruent to 1 mod 4. But it ain't. It's congruent to 3 mod 4. 3 or minus 1. It ain't. We know n is congruent to 3 mod 4. So you have to phrase this carefully. We're not so sure about an arbitrary prime factor of n. But we know there must be at least one prime factor of n which is congruent to 3 mod 4. Because if they were all congruent to 1 mod n, n would have to be congruent to 1 mod n. But n, by the way we've constructed n, is definitely not congruent to 1 mod n, because it's 4 times something minus 1. So it's congruent to 3. Has at least one prime factor q, satisfying q congruent to 3 mod 4. i.e., q is equal to 4m minus 1 for some n, for some integer n. But we already said here that q is strictly bigger than p. And p was special. P was supposed to be the biggest such prime. But now we've encountered another one which is bigger than p. So we've contradicted ourselves. So these things is a contradiction. So those two statements there, that q is 4m minus 1, q is a prime, and q is strictly bigger than p, that contradicts p being the biggest such. Now, there was nothing wrong with the various steps of the argument there after we introduced p. Here we introduce p is the biggest such prime. From that point on, you can criticize the presentation of it maybe, but there's nothing wrong with the logic of it. The logic is solid from that point on. It's rigorously argued. You can't fault any of the logical steps, yet we arrive at a contradiction. Okay? So it must be impossible to talk of this p. It must be impossible to mention the largest such prime of this. So that means there is no largest one. And there's at least 3 of them. So therefore there must be an infinite number. Because if there's only a finite number, there would be a last one. And we could at least hypothetically speak of it. And we shouldn't reach a contradiction based purely on just mentioning this largest subprime. So this is a contradiction, so therefore there are an infinite number of them. So that's an example of an adaptation of Euclid's original proof to a different setting, to looking at a certain arithmetic sequence, not the whole sequence of integers, but the sequence of integers congruent to 3 mod 4, congruent to -1 mod 4, however you like to say it, and proving that there's an infinite number of primes in there. And there are a few of these special cases where, with the machinery we've developed up to now, it's possible to say, it's possible to prove that there's an infinite number of them. Okay. Any questions about the way the proof went, or any clarification I can give to you on it? Okay, so let's look at another case. So part B is one. Now this is one that's going to involve quadratic reciprocity, which you might tell by looking at the form of the way we construct the n here. So this is the arithmetic sequence of things congruent to 3 modulo 8. Part B is the statement there are an infinite number of primes P of the form P equals 8k plus 3. K in the instance. Okay. So this is the claim. So you recognize this as a special case of Dirichlet's theorem, because the 3 and the 8 are co-prime. Here we're using A equals 3, and the n in the original statement of Dirichlet's theorem is 8. There's certainly a few primes of this form. P equals 11 is 1. You could say P equals 3 is 1, 11 is 1, 17 is 1. There seems to be loads of them. 25, 33, 41. 41 is prime. Yep. So there seems to be plenty of them. Again, don't be fooled by there seems to be a lot of them early on. I mean, most numbers of that form are not prime. Most integers are not prime. There's a fair few in the early stages, but they get rarer and rarer as you go. But the claim is that there's an infinite number. And we did that. We don't know that yet. We know there's an infinite number of primes in all of the integers. But what about in that congruence class? So the 3 is co-prime to the 8. So we certainly can't point to a trivial factor that will always divide a number of that form. So here's how the argument goes. So again, it's another adaptation of Euclid's argument. So there's at least a few of them. So suppose there's only a finite number. Let's call them P1 has to be 3, P2 has to be 11, and so on, up to PS. So suppose that's the complete list of primes of this form. What we want to do is squeeze a contradiction out of that. Now, it's not as easy to come by as it was in the case of 4n minus 1. But we can still get one along the same lines, but the number we speak of is, now we include 2. We multiply together all these primes, we add in a factor of 2, we square it, and then we add 2. Now, the reason why we construct the n like this, it'll become apparent. This is a construction of n that will work, that will yield a contradiction for us. But, I mean, how they happen to bond this, or how you know that this is the correct n to look at, you'd have to get there by kind of a matter of trial and error, or, trying different approaches. Now, the reason you can kind of see a clue to the fact that we're going to have to talk about quadratic residues because we're squaring some. So in the construction of n, we're taking this product of all the primes and we're squaring them. So that's going to introduce at least the concept of quadratic residues. Hang on, why did I add in the 2? Sorry, I was looking at the wrong thing. We don't add in the 2. Excuse me. I was looking at the previous thing. So we don't add in the 2. Just take all those primes, multiply them together, square them, add 2. First of all, notice n is odd. Is that easy to see? Well, you see all the primes are odd. Yeah. When you multiply odd numbers, you get an odd number. When you square an odd number, you get an odd number. When you add 2 to an odd number, you get an odd number. Okay? So you can see from the way that n is constructed that n is odd. So there exists an odd prime q such that q divides n. Q is odd. Now, what does that say about q modulo 8? Well, it could be 1, 3, 5, or 7. Okay, because those are the odd congruence classes modulo 8. It can't be 0 mod 8, or 2, or 4, or 6, because that would be an even number. Okay, but q is odd. All the prime factors dividing n have to be odd. Okay. Now we're particularly interested in this 3 case. We want q to be congruent to 3. Because then this will be another prime number congruent to 3, and it can't be any of those ones. Because if q was one of these ones, it would divide n and divide this, so then it would have to divide 2. And that would be a contradiction. So we want to zero in on this q congruent to 3 case. Now, if q divides n, that means q divides this big bracket squared plus 2. So that implies that this big bracket squared plus 2 is congruent to 0 modulo q. Or in other words, minus 2 is congruent to this big bracket squared modulo q. So that we recognize as making a certain claim about a quadratic residue modulo 2. Therefore, minus 2 is a quadratic residue modulo q. Or in terms of our Legendre symbols, minus 2 q equals plus what? Minus 2 mod q equals plus 1. Everybody okay with getting to that statement? Yeah. I haven't bothered to fill in, so what's inside the bracket is all those primes multiplied together. I'm not so interested in that in this stage. It's just that there's something that when you square it, you get minus 2. Okay, so minus 2 is a quadratic residue. Now,
what could you do with this Legendre symbol? Is there any way you could simplify that or expand it, that Legendre symbol?
Break it up.
Into
Of minus 1 and 2.
Yeah. So that's equivalent to saying minus 1, the Legendre symbol minus 1 mod q, the Legendre symbol 2q, but they multiply together to give plus 1. Because remember, the Legendre symbol, considered as a function of the first argument, is a multiplicative function. So if you factorize the first argument, you can factorize the Legendre symbol. So the justification for that step is since this thing is a multiplicative function. Remember, that's a key property we use in our algorithm for determining Legendre symbols, the factorize, flip, reduce algorithm. You're always using the factorize property. Now, the Legendre symbol of minus 1 modulo prime, the Legendre symbol of 2 modulo prime, you should recognize those because we proved results about those. We completely understand when and how these take the values plus 1 or minus 1. This one depended on q mod 4. This one depended on q mod 8. So if we get information about q modulo 4 and 8, hopefully we'll be able to draw this conclusion that q must be 3 mod 8. But how can it be that when you multiply these two, you get plus 1? Well, that can happen in two ways, yeah? Either they're both plus 1 or they're both minus 1. There's two ways in which this can happen. Either they're both plus 1 or they're both minus 1. They can't be the opposite of each other. Can't be one of them plus 1 and one of them minus 1 because then you'd have minus 1 as the product. Yeah. So now we can call upon those lemmas. They were consequences of Euler's criterion, remember? They were lemmas theorems 8.5 and 8.6. But theorems 8.5 and 8.6, well, we look at the consequence. If minus 1 is a quadratic residue, that means q is congruent to 1 mod 4. And if 2 is a quadratic residue, it means q is congruent to plus or minus 1 modulo 8. Or they could both be minus 1. If minus 1 modulo q is not a quadratic residue, that was the same as saying q is congruent to 3 mod 4. Yeah. And if 2q is minus 1, that was q being congruent to plus or minus 3 mod 8. 3 or 5. So that's congruent to 3 or 5. This is congruent to 1 or 7. Okay, so it's either this or this, but each condition is an and. So try and examine each of the two conditions, the top condition and the bottom condition. Can we consolidate them into? So if something is 1 mod 4, and you also know it's 1 or 7 modulo 8, can you boil that down into just a single condition? So it's the same q we're talking about. So how can it be that q is congruent to 1 mod 4 and congruent to 1 or 7 modulo 8? Can we remove that ambiguity?
The Chinese, so as we stated that the Chinese remainder theorem only applied when the moduli were coprime, which they're not. Maybe something simple. So the ambiguity is here. I mean, that's unambiguous.
Would that be on the cube? Would that be 1 or 5? Could you write that as 1 or 5 mod 8? 1 mod 4.
Yeah, so if you're 1 mod 4, how do you appear mod 8? That's the point. If you're a multiple of 4 plus 1, well, either that multiple of 4 has a 2 in it, so it's a multiple of 8 plus 1, so you're congruent to 1 mod 4. Or that multiple of 4 does not have a 2 in it. So if you divided it by 8, so it's an odd multiple of 4. So 8 goes in a certain number of times, but then there's 1 4 left over. So if you divide it by 8, you get 5. Or another way to see it is ask yourself, could Q be congruent to 7? If you're congruent to 7, what are you modulo 4? Yeah, 3. Because if you're a multiple of 8 plus 7, when you try and divide yourself by 4, the 4 goes in an even number, an integer number of times into the multiple of 8, leaving a remainder of 7. But when you divide 7 by 4, you get remainder 3. So 7 mod 8 and 1 mod 4 are incompatible. You can't be both. So the only way for these two conditions to be true is if you're 1 mod 8. So that top line is equivalent to saying you're 1 mod 8. As 7 is congruent to 3 mod 4. That's basically the reason. 4 divides 8. Yeah. And what about the bottom line? Which is the one that survives, of the 3 and the 5, which one survives on the bottom line? Sorry? The 3. Because 5 is congruent to 1 mod 4. So if Q is congruent to 3 mod 4, it can't be congruent to 5 mod 8. Everybody okay with that? How did we finish the argument? So at the moment, what do we know? We pretended there was a finite number of primes. Remember, they're all congruent to 3 mod 8. Remember? We pretended there's a finite number of them. We constructed this n. We argued n must have a prime factor, and I forget all the intermediate stuff. N must have n has prime factors q, and these prime factors q are either 1 mod 8 or 3 mod 8. Now it's the 3 mod 8 case we're interested in. Because if we can decide that there is a prime factor of n, which is 3 mod 8, then we'll get a contradiction. Because that q then must be listed in this list in here. So q divides n and q divides the bracket, therefore q divides 2. That's a contradiction. Because the only prime dividing 2 is 2. And this is a number that's congruent to 3 mod 8. So if we can argue that there must be a prime factor q congruent to 3 mod 8, then we've got our contradiction. But we're not quite there yet because it's 1 mod 8 or 3 mod 8. How do we know that the 3 must arise? Sometimes. Well, n is congruent to what modulo 8? Can we decide what n is modulo 8? Well, we know what the p's are congruent to. Each of the p's is congruent to 3 mod 8. So what happens when you multiply a load of them together and square?
Yeah, one mod.
Yeah, because, well, if instead of multiplying them all together and squaring, square each one and multiply the squares together, yeah? So the square of a product is the product of the squares. And when you've got something congruent to 3 mod 8 and you square it, as Joshua said, you get 1 mod 8. So each p squared is congruent to 1 mod 8. You multiply together a load of things that are 1 mod 8, it's 1 mod 8. And then finally we add a 2. So n has to be congruent to 3 mod 8. That's the point. N is congruent to 3 modulo 8, since each pi squared is congruent to 3 squared, which is congruent to 1 mod 8. Each pi was congruent to 3 modulo 8. So you multiply together a load of things that are 1 mod 8, and then finally you add 2. So you've got 3 mod 8. Does that help us? So n is 3 mod 8, and every prime factor is congruent to 1 or 3 mod 8.
Well, if n is congruent to 3 mod 8, then you can't have something that's 3 mod 8 going into the
Don't seem to be getting that out of you. So this is the one we want to identify. We want to say that this has to happen at least once.
Is it when that's equal to that? Or Q is equal to that itself?
But we don't know. I mean, n is probably not a prime number. So again, we have to do a quick little proof by contradiction. Suppose this case never happened, right? But then all the prime factors of n would have to be 1 mod 8. Yeah? But a number is the product of its prime factors. So if all prime factors of n were 1 mod 8, n would be 1 mod 8. Because n would be a product of all of these q's, sometimes with repetitions, perhaps, if the q divided it with multiplicity. But n would be a big product of a load of prime numbers that were all congruent to 1 mod 8, so n would be congruent to 1 mod 8. But it isn't. It's congruent to 3 mod 8. So it must be that there's at least one of these cases. Because otherwise, n couldn't be congruent to 3 mod 8. If all, so we just want to say that, so if all prime factors q of n had q congruent to 1 mod 8, then n would be congruent to 1 mod 8 also. Because n is a product of all those products. But n is 3 mod. So there is at least one q such that q divides n. Well, if they can't all be 1 mod 8, at least one of them must be 3 mod 8. So this is our interesting prime number q, because if q divides n, and if q is congruent to 3 mod 8, that implies q is equal to pi for some i. 1 up to s. Okay, because remember, governing all of this is the assumption that there's only a finite number of these primes. It's the p1 up to ps. So if q is congruent to 3 mod 8, it must be one of those p's. But now, this will imply that q divides n minus the product of all the pi's squared. But when you subtract the square of this bracket from n, you get 2. That implies q is equal to 2. Q is a prime number, dividing 2 has to be equal to 2. But now this is a contradiction. Q can't be 2 and come to 3, not 8. Shocked face. Okay, contradiction. So again, with all these proofs by contradiction, either you've stumbled upon the contradiction in the heart of the universe, or you haven't done that, you've made a mistake. You look back at your argument, you have to have made a mistake, otherwise everything collapses. But it all looks good, it's all fine, except for the very first sentence. The very first sentence was a mistake. You cannot speak of the complete list of all of these primes. Because if you do speak of that complete list, you arrive at a contradiction. This is a contradiction. So there is no finite list of primes of the form 8k plus 3. And there's at least 4 of them. We listed 4 of them at the start. So if there's no finite list of them, then there must be an infinite number. So again, that's another special case of Dirichlet's theorem, which we needed. Okay, we didn't need quadratic reciprocity, but we needed the concept of quadratic residues and the consequences about -1 and 2 that we got from Euler's function. Again, you can see how it's inspired from Euclid's proof. Assume there's a finite number of them, construct this appropriate n, examine the prime factors of n, reach a contradiction. That's how Euclid's proof went, and that skeleton still fits this proof. Okay, the intermediate details are somewhat harder and more involved, but you again get a proof like this. Now, unfortunately, it's not possible. It's not possible for every a and n. It doesn't seem to be possible to construct a kind of simple enough proof like this. For certain choices of a and n, we can get the technology we have to prove that there's an infinite number of primes there. But it doesn't seem to be, you seem to need some deeper theoretical understanding to prove the general case, to prove it for all those cases. So that would be what, if you were to take this study further, what you would, one avenue you could go down, developing the tools in order to prove Dirichlet's theorem. And it kind of says to me anyway that there's an infinite number of primes, all right, and they're distributed everywhere. Everywhere meaning in every congruence class that they could be in. They can't be in a congruence class that's obviously composite, where the representative and the modulus share a common factor. Because then those are all divisible by that common factor. But as long as the congruence class is not obviously composite, you will find an infinite number of primes. So the primes are distributed everywhere without any kind of bias. And indeed, I believe there's statistical analysis as well, and statistical and results that there's the primes in these arithmetic sequences have the same density as each other, I think. Maybe I'm stepping too far. You can speak of the density of the primes in these, how the density of the primes in these evolves as you look further and further out along the sequence. What's the long-term asymptotic limit of the density? So there might be also interesting results there as well. Okay, there's another case for you to try. There's the part C there, 6k plus 1. You could have a go at solving that yourself. I believe also 6k minus 1 might also be approachable. So try question 3, part C, and maybe the case of 6k minus 1 is also doable. I believe, if I haven't included it there as an exercise, but that might be one for you to try and do as well. And I'll see you next week for a lecture and some more tutorials next week, okay? But I think that might kind of be the end of the fresh material. I think we'll kind of switch back now into revision mode a bit and start going back over some of the exercises, maybe bringing in further practice exercises as well to look at, but with having our focus being revision, okay?
How do you say his name?
Dirichlet, French, I think.
Never pronounced that.